All right, let's jump right into this explainer and decode the morphology of flowering plants. If you're prepping for exams, you already know this stuff is absolutely crucial, but man, it can feel like a giant mountain of pure memorization. Well, today we're going to change that. We're building a logical, visual framework so this information actually sticks.
Our source material uses a brilliant analogy for this. Think about it. Studying aimlessly is literally like wandering around a massive mall. You get totally distracted by things you just don't need. Instead, you need to treat this like a quick trip to your local Kirana store, a neighborhood grocery with a super strict shopping list. You grab exactly what you need and you get out. So consider this explainer your high-yield shopping list. We're skipping all the low-yield filler today.
So here's the game plan for our journey today. First, smart study and plant basics. 2, roots, anchors, and modifications. 3, stems, shoots, and survival. 4, leaves, venation, and modifications. And finally, number 5, inflorescence and the flower. Let's kick things off with Section 1, Smart Study and Plant Basics. Right out of the gate, the absolute most crucial thing to understand is that stems and roots play by totally different structural rules. Stems develop from the plumule of a seed, whereas roots come from the radicle. But here's the golden rule, the one trick to identify any plant part. Stems always have nodes and internodes. Think of nodes as the specific little spots where leaves or branches attach, and internodes as just the space between them. Roots, they completely lack these nodes and internodes. Keep that rule in your back pocket because it's going to solve a ton of trick questions for us later on.
Moving underground, let's hit Section 2, roots, anchors, and modifications.
If we zoom way in on the very tip of a primary root, we actually see 4 distinct growth zones. Down at the very bottom is the root cap. It's basically a protective helmet that shields the root as it bulldozes through harsh soil. Right behind that is the meristematic zone, which is just packed with small, super rapidly dividing cells. Above that is the elongation zone, where those cells literally stretch out to drive the root deeper. And finally, the maturation zone, where cells mature and develop tiny root hairs to suck up water. Now here's a high-yield fact to jot down. Aquatic plants, like Pistia, don't have a root cap at all. I mean, they're growing in water, so they don't need to push through hard dirt. They use root pockets instead. Okay, let's talk about the primary taproot. That's the main root growing straight down from the radicle, and how it actually modifies itself for extreme survival. First up, food storage. Taproots can get really thick and fleshy. Honestly, that's exactly what a carrot or a radish is. Second, and they love to test this one, modifications for respiration. In swampy marshlands where the mud has zero oxygen, plants like Rhizophora develop pneumatophores. These are roots that literally grow upwards, popping right out of the ground to breathe the air. Crazy, right? And third, taproots can develop little nodules to house bacteria for nitrogen fixation, which is exactly what we see in legumes. Now, what's really fascinating is how adventitious roots adapt. By definition, an adventitious root is just any root growing from somewhere other than the radicle, like straight out of a stem or a leaf. And they are incredibly versatile. For storage, think of a sweet potato. For massive physical support, you've got those giant hanging prop roots on a banyan tree, or the stilt roots propping up a maize stem. Some even turn parasitic. The Cuscuta plant actually develops adventitious roots that physically stab into other plants just to steal their nutrients. All right, time to head above ground for Section 3, stems, shoots, and survival. Above ground, the stem's growth is driven by buds, specifically axillary buds that sit right in the angles of the leaves. It is amazing how these axillary buds can totally transform for survival. Instead of just turning into a normal branch, an axillary bud can stretch out into a springy, coiling tendril to help vines like gourds and grapes climb up toward the sun. Or if the plant needs some armor, that exact same bud can harden into a sharp, woody thorn to fight off hungry animals, like you'd see on a citrus plant or a bougainvillea. And out in the brutal desert, the main stem can actually flatten out into a fleshy green structure called a filiclade. You see this in the opuntia cactus, where it's perfectly adapted to store water and do all the photosynthesis when leaves aren't around. And this brings us right back to why our golden rule from Section 1 is absolutely essential. Consider these underground modifications. Things like potatoes or ginger live underground, right? So naturally people assume they're roots, but actually they are underground stems. How do we know for sure? Because they have distinct nodes and internodes. Those little eyes on a potato? Yeah, those are nodes. Above ground, we also see subaerial stems spreading out horizontally. You've got the offset in aquatic water hyacinths, runners spreading through your grass, or suckers shooting up diagonally in banana plants. Moving further up the plant, let's get into Section 4, leaves, venation, and modifications. Let's focus on the surface of a leaf blade, or the lamina.
Venation is just the arrangement of veins across the surface. And guys, this is a highly testable concept because a quick glance at those veins instantly tells you the evolutionary category of the plant. If the veins form this messy, branching network, which is called reticulate venation, you're looking at a dicot plant. But if the veins run in neat, straight, parallel lines side by side, you're dealing with a monocot, like grass or bamboo.
Next up is phyllotaxy. Simply put, this is the pattern of how leaves are physically arranged on the stem. The plant's ultimate goal here is just to catch as much sunlight as possible without the leaves shading each other out. There are three main patterns to remember here. First is alternate, where you just have one single leaf per node, alternating sides as you go up. This is definitely the most common. Then you have opposite, where two leaves pop out at the exact same node, facing directly across from each other. And finally, whorled, where more than two leaves circle around a single node in a little group. Just like roots and stems, leaves can completely change shape to survive. Definitely add these to your mental shopping list. For support, leaves can morph into climbing tendrils, like we see in the pea plant. For defense and to save water, leaves can shrink all the way down into sharp spines. That's literally what cactus spikes are. For storage, well, this one is super fascinating. The thick, juicy layers of an onion that you chop up for dinner, those are actually highly modified storage leaves. And finally, for trapping. Plants growing in super poor soils, like the pitcher plant, modify their leaves into literal physical traps to catch and digest bugs for extra nutrients.
And finally, we reach the top of the plant. Section 5, inflorescence and the flower.
Before we dissect a single flower, we've got to understand how groups of flowers are arranged. This is called the inflorescence, the arrangement of flowers on the main floral axis. The big takeaway here is that a flower doesn't just magically pop out of nowhere. Structurally speaking, a flower is really just a highly modified, condensed stem. The apical bud basically stops making normal leaves and switches over to making floral appendages instead.
So, how does this actually grow? It builds into two very distinct architectural patterns. First, we have the racemose inflorescence. In this setup, the main axis just keeps growing indefinitely. And because it keeps stretching upward, the oldest, largest flowers are left behind at the bottom, while the brand new buds form at the top. On the flip side, we have the cymose pattern. Here, the main axis actually stops growing because a flower blooms right at its very tip. That caps the growth entirely, forcing any new flowers to branch out below it. That means the oldest flower is always sitting right there at the top. Grasping the difference between these two is absolutely essential for categorizing floral families later on.
Okay, let's zoom in on the flower itself and look at the male reproductive powerhouse, the androecium. It's made up of individual units we call stamens. Each stamen has a long stalk, the filament, topped by this little sac-like structure called the anther. Inside this anther is where the real magic happens. It houses the microsporangia, which eventually develop into pollen grains. Oh, and a quick vocab word to remember. If a stamen is sterile and just can't produce pollen, it's officially called a staminode.
All right, let's do a quick active recall check to see if these structural rules are clicking. Think about a standard maize cob, an ear of corn. If you look closely at how it grows, the oldest, largest seeds are down at the thick base, and the younger, smaller ones are way up at the tip. So based on that arrangement, which growth pattern does that match? Take a second. All right, let's do a quick active recall check to see if these structural rules are clicking. Think about a standard maize cob, an ear of corn. If you look closely at how it grows, the oldest, largest seeds are down at the thick base, and the younger, smaller ones are way up at the tip. So, based on that arrangement, which growth pattern does that match? Take a second.
And just like that, we've checked off every high-yield item on our strict Kirana store shopping list today. The source material heavily points out that the next big step is applying these very rules to major floral families like Solanaceae and Fabaceae. So ask yourself, are you ready to tackle and draw out those exact floral diagrams from memory? But hey, before you dive back into the books, just take a step back from exam mode for a second. Every single thorn, every tendril, and every flower we explore today is a real-time record of a plant literally engineering its own survival. Next time you see a simple potato or chop up an onion for dinner, just ask yourself, what other hidden survival strategies are happening right beneath our feet? Keep reviewing this framework, and I will see you in the next explainer.